I want to talk about triple integrals in rectangular coordinates, but I thought we'd start by taking a tour of how we defined the definite integral for functions on one variable, the double integral for functions on two variables, and use the same kind of thinking to define a triple integral for a function on three variables. So for functions on one variable, we have an interval in the domain from a to b. And the idea was we chopped this interval up into some number of subintervals. Typically we called that n subintervals. We called each little subinterval length a delta x. Sometimes we even pretended that they were we would assume they had the same length, but they don't have to, right? They could be whatever length we chose. And then we computed a function value based on a sample point that we would choose in each interval. And that x sub k could be any point, the left endpoint, the right endpoint, the midpoint, or any point between those points. And then we would form a sum from k equals 1 to n. And then to define our definite integral for functions on one variable, we took a limit as n approaches infinity of that Riemann sum. And another way to think of that is instead of saying n goes to infinity, we could say the width of the smallest subinterval goes to 0. This was the definite integral, and a lot of the times, we'd think about a to b being on the x-axis, and then the sample points evaluated in a function gave us the height of a rectangle. And so we thought of those as areas. But we certainly don't have to understand this definition. We just chopped the domain up into little subintervals, picked a sample point, computed a function value, multiplied it by width, add all that stuff together. Okay. For functions on two variables, we kind of did the same thing. We're going to divide the region we're integrating over. Here it was a length, now it's an area. We divided it into a bunch of smaller little parts. Instead of subintervals, now we have little rectangles. And I've drawn a bunch here that look like squares, and they might all have equal width, but we know they don't have to. And we called each little area there a delta A sub k. In each one of those little rectangles, we picked a sample point. We computed a function value at that sample point, so f of xk, yk, times that little delta A sub k. And we added all of those together. And then we said, hey, let's let the number of little sub-rectangles go to infinity, or the delta A sub k that's the smallest could go to 0, and that was our definition of a double integral. And now we're to our real goal, to talk about functions on three variables. Well, now my integrand has three domain variables. My region, I'm going to call B this time, just for the heck of it, will live in the domain, which is now some region of space. Right? Three domain variables means my domain itself lives in space. So some three-dimensional region like that. Well, okay, so I'm integrating over a length, so dx. Here I'm integrating over an area, so dA. And here I'm integrating over what clearly would hold a volume. So I think that's going to end up being a dV. I need to chop this up. So I had length areas. I need to chop this region B up into a bunch of little volumes. So here I just drew a bunch of, put a bunch of endpoints down to break up that into subintervals. Here I had to draw a bunch of lines to chop this up into rectangles, and here I would have to kind of do it 3 times to chop that up into a bunch of little rectangular prisms. Now that would be real hard to draw, so I'm not even going to try, but I'm going to imagine one little rectangular prism in there. So we're just dividing this up like we stacked a whole bunch of boxes in that region. Now if I drew that better, right, my box would have dimensions that were parallel to the x, y, and z axes. So let's try that one more time, maybe with a little more attention to scale. Something more like that, still not great. But regardless, I'm just thinking about little rectangular prisms to subdivide that space, like I stacked up a bunch of boxes. Well, I'm going to approach it the same way, right? I partition into little intervals. I partition into little rectangles. I partition into little boxes. And then inside each little subinterval, I take a point. Inside each little rectangle, I take a point. And inside here, inside this little rectangular prism, I take a point. And I do that in every little rectangular prism that would fill that region B. Well, that little point would be a xk, yk, zk. The volume of each box I could call delta V sub k. And then I could form the same kind of Riemann sum. The triple integral over the region B of f of x, y, z with respect to V is the sum, the limit of the sum from k equals 1 to n of f of xk, yk, zk, delta v sub k. So I'm integrating over volume. So when I thought of my single integrals of functions on one variable, right, I thought of the answer as being an area, right, because I had a height times a little width. Here, if I had a function over the region R that was positive, I thought of this double integral as a volume. And here, well, I would need a fourth dimension. I plugged in a point from x, y, z into a function to get a w. And so right now I can just understand it using this definition, but it's what we would call a hypervolume, right? It would be the volume of an object that existed in 4 dimensions. And that's just a little tough to think about, and we might spend some time trying to understand that better, but right now we can think of this as a process. Even better news. If the region B were itself a rectangular prism, that is, it had nice bounds that look like these, and being a little bad here, I'm using the letter E as any real number, not the special number E, and I typically wouldn't do that, but we'll just let that go for now. I can rewrite this as an iterated integral. And because it would be a rectangular prism, I could actually do it in any order I chose, because if I take the integration in pairs, I can think of Fubini's theorem as applying. And so my triple integral can also be an iterated integral. And in fact, if I do one round of integration, now I'm down to just a double integral, and I could definitely use Fubini's. And so that kind of thinking would always apply, even over general regions. Now for Fubini's theorem in the plane, right, we could always think of a top function or a bottom function in the plane, or a left function and a right function, or the sum, right, additive regions that would behave that way. For triple integrals, we have to be a little more subtle in how we approach it, because my functions are now going to be maybe z equals, which would be a top and a bottom of a surface in space, or a y equals, which would be kind of a left and a right like that, or an x equals, right? So there's many, many different ways of setting these up. In fact, if I just think about how many ways I can arrange dx, dy, and dz, there'd be 6 ways of doing that. So every triple integral we ever encounter, if we want to rewrite it as an iterated integral, there might be 6 different ways to do it, and it might be up to us to try to figure out which way is the best way. In our next video, we're going to talk about how to find bounds for an iterated integral to evaluate a triple integral. And in between that video and this video in our Moodle course, you'll actually find this handout, which is the way I like to think about finding these bounds. There's also a procedure in your textbook, but this is the general procedure I try to follow.